Friends, in the previous session, we have discussed the definition of Turing machine and designing a Turing machine for a given language. In this session, we will discuss how to design Turing machines for some more given languages. Let us see the first language. To design a Turing machine that accepts a language L containing the strings of zeros and ones having the substring 001. For such type of languages, to design a Turing machine, we need to first design deterministic finite state machine. So the deterministic finite state machine for this particular language is starting with state Q0, 0, 0, 1 reaches the final state. Before and after you may have any string. So how to design this DFSM in detail? You can go through the video lecture of designing deterministic finite state machine. So right now, once we have a DFSM with us, then its equivalent Turing machine will be initial state is Q0, equivalent Turing machine initial state is Q0. While reading the input string in the Turing machine, go on moving towards the right until you come across a blank. Q0 0 is going to state Q1. Its equivalent transition in Turing machine is Q0 for 0 is kept as it is, move towards the right and go to state Q1. Similarly, Q0 1 is taking a self loop. So Q0 1 1 move towards the right, be in the self loop or same state Q0. Coming to Q1, Q1 0 is going to Q2. So 0 0 R goes to Q2. Q1 1 Q1 for 1 keep 1 as it is, move towards the right, go to state Q0. Similarly, Q2 0 self loop, Q2 1 goes to Q3. Q3 takes a self loop for 0 and 1. So Q3 takes a self loop for 0 and 1. Once the string is over, then Q3 will come across a blank. At that time, keep the blank as it is, move either to the left or to the right and change the state. This state will be the final state. That's it. So this is a Turing machine which is equivalent to your deterministic finite state machine. So let us see the complete definition of the Turing machine. M is equals to Q summation tau delta Q0 BF. Q consists of Q0, Q1, Q2, Q3 and Q4, where Q4 is the final state. Summation is 0, 1. Tau is 0, 1 and B, where B represents the blank, and initial state is Q0 with the delta transitions. So let us check for a given string. Initial state Q0 pointing to the string 101001. This string contains the substring 001. Hence a string must be accepted by the Turing machine reaching the final state Q0. So let us see. Initially Q0 is pointing to the first symbol, that is 1. So Q0 1 is taking a self loop, keeping 1 as it is. So 1 kept as it is, move towards the right, be in the same state Q0. Next, Q0 0. So this will be the first 0. So it will change the state from Q0 to Q1 and move towards the right. So the derivation obtained is keep 0 as it is, move towards the right, change the state from Q0 to Q1. Next, Q1 1. Actually, after the first 0, we must get 0 itself, whereas here we got 1. So Q1 1 will go back to state Q0 and move towards the right. So the instantaneous description obtained is Q1 is changed to Q0, 1 is kept as it is and move towards the right, searching for the substring 001. Next, Q0 0. So being in the state Q0 0, it will change the state from Q0 to Q1 for first 0 of the substring 001. So Q0 is changed to Q1, 0 is kept as it is, move towards the right. Next, Q1 0. When you come across Q1 0, it means it is the second 0 of the substring 001. Change the state from Q1 to Q2. Keep 0 as it is, move towards the right. The instantaneous description obtained is Q1 is changed to Q2, 0 is kept as it is, move towards the right. In the right, we have 1, that is Q2 1. So that will be the third symbol of the substring. Hence, Q2 for 1 will change the state from Q2 to Q3, move towards the right. The instantaneous description obtained is Q1 is kept as it is, just change the state from Q2 to Q3 and move towards the right. Now in the right, at the state Q3, if we come across a blank, then it means we have a substring 001 in the string or the given string. Hence, it will change the state from Q3 to Q4, where Q4 is the final state, move towards the left or right. Since the state has reached the final state Q4, hence the string is accepted by this particular Turing machine. So let us see the next language. To design a Turing machine to obtain one's complement of a binary number. Given an input 011, 00011, interchange 0 to 1, 1 to 0. The output will be 1, 0, 0, 1, 1, 1, 0, 0. So here we need a single state Q0, which is the initial state, wherein if we come across a 0, replace it by 1, move towards the right and be in the same state. Similarly, if we come across a 1, replace it by 0, move towards the right and be in the same state until all the zeros are interchanged to 1 and 1 is interchanged to 0. Once the input string is exhausted and the initial state comes across a blank, then keep the blank as it is, move towards the right or left and change the state. The state which will be the final state, Q1. Hence the delta transitions obtained are at initial state Q0, for 0 change it to 1, move towards the right. or for a 1, change it to 0, move towards the right until initial state Q0 comes across a blank. If it comes across a blank, keep the blank as it is, move towards the right and change the state from Q0 to Q1, where Q1 is the final state. Finally, the Turing machine M is equals to Q summation tau delta Q0 BF is defined, where Q consists of two states Q0 and Q1. Summation is 0, 1. Tau consists of 0, 1 and blank. Blank is represented by B. Initial state is Q0 and final state is Q1. At last, let us check for a given string. Initial state is Q0. The input string given is 1001. So Q0 1, interchange 1 to 0. So 1 is replaced as 0. B in the same state, move towards the right. Again a Q0 0, replace 0 by 1. B in the same state, move towards the right. Q0 1, 1 is replaced as 0, move towards the right until we come across a blank. So we got a 0 here. So again 0 is replaced as 1. B in the same state, move towards the right. Now in the right you can see there is a blank. So once Q0 comes across a blank, then keep that blank symbol as it is, move towards the right and change the state from Q0 to Q1. Since Q1 being the final state, the string 1010 is replaced as 0101. So this is the complete definition of the Turing machine, which obtains one's complement of a binary number. Next, if we are supposed to design a Turing machine to obtain 2's complement of a binary number, usually what we do, given a number, we take 1's complement of it and then add 1 to it. That is, if the given input string is 01100010, then first we take the 1's complement of it, which is equal to 100111101. Then add 1 to it, which will be your 2's complement number. 0 carry 1, 1, 1, 1, 1, 0, 0, 1. This is indirect method. If I want directly, then given a number 011000010, then start from the right. If you come across a 0, keep as it is. If you come across any number of zeros at the right, keep those zeros as it is until you come across a first one. Once you come across a first one, keep that one also the same. And after that, interchange 0 to 1 and 1 to 0. So this is the direct method of obtaining the 2's complement. I repeat, from the right, if you come across a 0, keep those zeros as it is until you come across a first one. Once you come across a first one, keep that one also as it is and then interchange 0 to 1, 1 to 0. So this is the direct way of obtaining the 2's complement of a binary number. With this knowledge, let us design the Turing machine. At the initial state Q0 pointing to the first leftmost binary digit, we have to move towards the rightmost binary digit. So at Q0 state, we go for reading 0 and 1. Keep them as it is, go on moving towards the right until we come across a blank. Once we come across a blank, keep blank as it is, go to the left. And your state Q1 will be pointing to the rightmost symbol. Now as I explained, we have to check. If it is a 0, if the rightmost binary digit is a 0, then keep that 0 as it is, move towards the left. You may have any number of zeros. All those zeros must be kept as it is and go on moving towards the left until you come across a first one. Once you come across a first one, keep that one also as it is and change the state. Move towards the left. So once you have changed the state to Q2, it means what first one is kept as it is. Now from Q2 onwards, it will be just 1's complement. That is, if you have a 0, replace it as 1, move towards the left. If you have a 1, replace it as 0, move towards the left. So go on replacing 0 as 1 and 1 as 0 and be in the same state Q2 and move towards the left until you come across a blank. So once you come across a blank, then just move towards the right and change the state Q3, which is a final state. So this is the Turing machine designed to obtain 2's complement of a binary number. So these are the delta transitions. Finally, the Turing machine is defined as M is equals to Q0, Q1, Q2, Q3, 4 states. Summation is 0, 1. Tau consists of 0, 1 and B. Delta transitions are given below. Initial state is Q0. Final state is Q3. Blank is represented as B. Let us take an example for a 4-bit binary number. Initially Q0 pointing to the number. Q0 1, keep 1 as it is, move towards the right. Go on moving towards the right until you come across a blank, keeping the state Q0 itself. So you can see here Q0 0, 0 kept as it is, move towards the right. Q0 1, 1 keep as it is, move towards the right. Q0 0, keep 0 as it is, move towards the right until you come across a blank. Once you come across a blank, change the state from Q0 to Q1. Keep blank as it is, move towards the left. Now Q1 is pointing to 0. So if Q1 is pointing to 0 means keep the 0 as it is, move towards the left, be in the same state Q1. Q1 1, it means this is the first rightmost one. So that one also must be kept as it is. Change the state from Q1 to Q2, move towards the left. Now Q2 0, 0 is replaced as 1. Move towards the left. Q2 1, again Q2 1, 1 is replaced as 0, move towards the left until you come across a blank. So once you come across a blank in Q2 state, change the state to Q3, move towards the right. Since Q3 is a final state, string 1010 its 2's complement is 0, 1, 1, 0. Let us see the next language to design a Turing machine to add two integers. Input is n number of ones followed by m number of ones separated by a blank, and output is n plus m number of ones. So the logic is very simple. Assume n is equals to 2, m is equals to 3. So the input is 2 ones followed by a blank, 3 ones followed by a blank. Finally, to get 5 ones, keep 1 as it is, go on moving towards the right. Replace this intermediate blank as 1. Remember, we have 1 extra. Then move towards the right. Keep m number of ones also as it is until you come across a blank. Once you come across a blank, move towards the left and replace the extra 1 by a blank. So finally, we are left with 1, 2, 3, 4, 5. 5 number of ones followed by a blank. So let us see the Turing machine for this language. Initially, we are at state Q0. So for n number of ones, keep ones as it is, be in the same state and go on moving towards the right until you come across a blank. So once you come across a blank, replace blank by 1, move towards the right and change the state. In this state, we go for reading m number of ones. So as I said, keep m number of ones as it is and go on moving towards the right until you come across a blank. Once you come across a blank, keep that blank as it is, move towards the left. Towards the left because we have to remove 1 extra, 1 and replace it as blank. So go to state Q2. In Q2, replace that 1 as blank. This 1 is replaced as blank. Move towards the right and change the state. And this state will be the final state. So this is the Turing machine for adding two integers. These are the delta transitions. So let us see for a given string where n is equals to 1 and m is equals to 2. Q0 1, so 1 is kept as it is. Move towards the right until you come across a blank. Next, once you come across a blank, change the state, replace blank by 1 and move towards the right. So Q0 is changed to Q1. Blank is replaced as 1, move towards the right. In Q1, all the ones are kept as it is and move towards the right until you come across a blank. So 1 kept as it is, move towards the right. 1 kept as it is, move towards the right until you come across a blank. So once you come across a blank, change the state from Q1 to Q2 and move towards the left. Then Q2 will be pointing to the last one, which must be replaced as blank. Change the state from Q2 to Q3, which is a final state, and move either to the left or to the right. The Turing machine halts at state Q3. Q3 is the final state. Input was 1 blank 1 1. Output obtained is 3 ones followed by a blank. So let us see a last language to design a Turing machine that accepts language L is equals to W raised to R, where W belongs to A comma B whole star. So the possible strings in this language are, if W is epsilon, then W raised to R is also epsilon. So the first string in this language is epsilon. If W is A, then W raised to R is also A. So AA is the next string. If W is a B, then W raised to R is also a B. So BB also belongs to this particular Turing machine. Next, if AB is W, BA is W raised to R. BA is W, AB is W raised to R. ABB as W, BBA as W raised to R. So ABB, BBA belongs to this particular language. So you can see here, if at all A or B exist, the string may start with A or it can start with B. If it starts with A, it ends with A. If it starts with B, ends with B. So using this feature of this language, we go for designing a Turing machine such a way that if W is epsilon, then so initial state for an epsilon string, that is for a blank, will go to the final state. The first one. Next, there are two possibilities. The string may start with A and end with A. I'll take up the same string, A, B, 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 A. Starts and ends with A. So at that time, replace A as blank, move towards the right until you come across a blank. Here I'll take blank as capital B, uppercase B. Once you come across a blank, then move towards the left. The last symbol must be compulsory A. Replace that A as blank. Next, if it starts and ends with a B, the same logic will be applied. Starts with B, B is replaced as blank. Move towards the right until you come across a blank. Once you come across a blank, move towards the left, that is the rightmost symbol of the string, which is compulsory B. B is replaced as blank. So these two will complete one cycle. Go back to the initial state and again check if it starts with A, then follow these rules. If it starts with B, follow these rules. Complete one cycle. Go back to the initial state. So this is the logic used. So using this logic, let us design the Turing machine. So initially we are at the state Q0. For a blank, go to the final state to accept the first string. Next, if it starts with and ends with a A, if it starts with a A, for the first A is replaced as blank. Change the state to Q1. In Q1, read all the other symbols present in the string and be in the same state. Go on moving towards the right until you come across a blank. Once we come across a blank, move towards the left and change the state. State Q1 is to read the intermediate symbols present in the string. Next, state Q2 will go back to the rightmost symbol. In Q2, the rightmost symbol must be a A if we have started with a A. This rightmost A is replaced as blank and move towards the left, change the state. So Q2 state will replace the rightmost A as blank and reach Q3. In Q3, we must keep the symbols as it is and go on moving towards the left until we come across a blank. So once we come across a blank, this completes one cycle. Keep the blank as it is, move towards the right and change the state back to the initial state. So this was if it starts and ends with a A. If it starts and ends with a B, the same steps will be applied. Initial state for a B is replaced as blank and change the state to Q4. In Q4, it will go for reading the intermediate symbols until it comes across a blank. So all the symbols A's and B's are kept as it is. Go on moving towards the right until you come across a blank. Once you come across a blank, change the state, move towards the left. Move towards the left to obtain the rightmost B. So once we get the rightmost B, replace that B as blank, move towards the left and go on reading the symbols in state Q3. Keep the symbols as it is, move towards the left until you come across a blank. So once you come across a blank, this completes one cycle of replacing leftmost B and rightmost B as blank and go to the initial state. And this will be repeated until we have any A's and B's in the string. Once all the A's and B's are over, Q0 after reading blank will go to the final state Q6. Hence, final Turing machine M is equals to Q0, Q1, Q2, Q3, Q4, Q5, Q6, where initial state is Q0, final state is Q6. Summation is AB and tau symbols are A, B and blank. And blank is represented by capital B. So this is the Turing machine designed to accept a language W raised to R, where W belongs to A or B whole star. Let us check for a string AB, BA. Since it starts with A, Q0 A is replaced as blank. Change the state from Q0 to Q1 and move towards the right until you come across a blank. Once you come across a blank in state Q1, change the state and move towards the left. State is changed from Q1 to Q2, move towards the left. In the left, Q2 must be pointing to a A. So this A will be replaced as blank. A is replaced as blank. Q2 is changed to Q3 and move towards the left. Go on moving towards the left until you come across a blank. Once you come across a blank, a cycle is completed. Go back to the initial state Q0. Now in state Q0 you can see the string starts with a B. So B is replaced by Q0, B is replaced by state Q4, B is replaced as blank, move towards the right until you come across a blank. Once you come across a blank in state Q4, keep blank as it is, move towards the left, change the state to Q5. And Q5 must be pointing to the rightmost B. If it is Q5B, replace B as blank, Q5 as Q3, move towards the left until you come across a blank. Once you come across a blank, then B3 is changed to Q3 is changed to Q0. A cycle is completed. Q0B, no more A's and B's. So state Q0 will go to state Q6 on seeing a blank symbol in the Turing machine. Q6 is the final state. Hence the Turing machine halts for the string AB, BA, accepting this particular string as it belongs to the language. So this is how we go for designing the Turing machines for the given languages. Thank you.